Alright, welcome to my third and final installment on my first lesson of U substitution for integrals. So let's take a look at two final examples for this lesson, okay? Now, taking a look at this integral first, integral of e to the x times cosine of e to the x dx, seems like something very difficult to solve because it's obviously something that we just don't solve directly using the tables and the knowledge we have so far, right? So that's a good place to ask yourself, can I use U sub? I'm going to analyze the options I have. One of them is I could pick u equals e to the x. Another one could be u equals cosine of e to the x. The third option would be to select the whole thing, but as I've been telling you in the previous videos, picking the entire integrand as your u is like 99% of the time not going to be useful. We're going to forget about that option, and we're going to consider either e to the x or cosine of e to the x. And ultimately, I'm going to be picking e to the x because notice that when first of all, it's easier to take a derivative of e to the x rather than cosine of e to the x, okay? The second thing is, like, du is e to the x dx, and the second thing is that once we have u and du, we can see that, e to the x dx, this whole thing is just du, and then cosine of dx can turn into cosine of u. And notice how easy this turned out to be, right? How easy this is, okay? This is just sine of u. And again, we have to go back to the x world. Don't forget that. It's just going to be sine of e to the x plus c. And we're done. All right, so for our final exercise, I have z squared over z cubed plus 1 dz, and I have a couple options over here. I could say u equals z squared or z squared, I call them interchangeably, z squared, but if I do du, it's going to be 2z, which is not going to be particularly useful for what I have on my denominator, so I'm going to forget about that option, okay? I could pick u equals z cubed plus 1, and that actually is a pretty good option. It's in fact the best option because then du is 3 z squared dz. I can go ahead and put the 3 on the other side. So du over 3 is z squared dc, which matches perfectly what I have over here. It's very convenient. However, I could have also picked, and let me call this u2. I could pick u equals z, just z cubed, and then du would also be 3 z cubed dz, which is also useful for this integral, okay? So du over 3 z squared dz, they're both as equally useful. So let me actually go ahead and solve it both ways and see what happens. So for the first one, for u1, let's call it u1, I'm going to have 1/3 integral of z squared dc, that's just du over 3, right? I already have the 3 here, so a du, and then 1 over u. And how easy is that, right? Just natural log absolute value of u, and we turn back to the x world, so natural log absolute value, this is u, so u equals z cubed plus 1 plus c. And I'm done because z cubed can output negative numbers if we input negative values to it. So I'm just going to leave the absolute value bars instead of deleting them. Okay, awesome. Now let's take a look at our second method. When we do it this way, we have the integral of, now z squared dc, in this case, it's going to be, once again, 1/3 du, and then I have 1 over z cubed is u. There's nothing for the 1, so I have to put u plus 1. I'm going to have to do that. And now when we see this integral, the integral of 1 over u plus 1, right, if you have a little bit of experience, then you can say, oh, this is easy. This is just 1/3 natural log absolute value of u plus 1. That's easy because there's a linear term denominator that we're integrating. But technically, in order to do this, you do have to apply u substitution, okay? So you could say here, I could pick another variable, v. Let's say that v equals u plus 1, and then dv is going to be du, and then you need to rewrite this integral would be that 1/3 integral of u over v dv, and you can see over here this is just going to be 1/3 natural log absolute value of v, which is u plus 1, which matches perfectly with what I have over here. So technically we do have to apply substitution once again, and that's why I would say that this is by far the most convenient option. You can just make a substitution once and you're done. In this other method, you technically have to substitute twice in order to put it in the simplest possible form and finish it. However, we can argue that with a little bit of experience, we can look at this and integrate it directly, consider it as an indirect integration, or I'm sorry, as a direct integration. So that's cool. I'm just gonna finish this off, and I said that u2 was said cube. So, and that part matches perfectly with what we have over here. How cool is that? So this is an example of an integral that you can solve it like more than one way using u sub in this case particularly, and that's awesome. So I'm just going to stop here. I think this is more than enough for you to practice. Go ahead and take a break and then practice on some more exercises with u sub. And after this, you are now ready for my next lesson, which is going to be about integration by parts. So I'll see you there. Bye-bye.